I'm here to talk about codifying the practice of distributed coding at scale. I do terabyte scale coding at Mozilla, data engineering, and I'm here to offer some help and to ask for some help. The help I'm going to offer you is a specific mental model of how to do distributed coding at scale so that you don't get stuck and you're productive. Because in the small coding community I've come from, we found that learning on the job was very inefficient, that there were techniques that although among us we'd coded in dozens of different environments and previously expected to pick up a new environment, a new language very quickly, that we were encountering new categories of problems that would cause us to lose time. And I'd like to codify that and transmit it to y'all to save you time. And then the help I'm going to ask you for is to evaluate this model. And if you haven't done this kind of coding before, that's okay. I'd like to know, does it make sense? Is it clear? And for the dozens, if not hundreds of you who have done this coding before, I'd like you to evaluate it against your own experience. Because this is anecdata, right? This is one community's experience. We've validated it internally. But the range of environments and techniques y'all have used are much, much bigger. And so I'd like to get to a point where we can collectively turn these skills into things that are easily and quickly transmitted so that we can all be productive and effective. So let's begin with a model for normal coding. Normal. Here's a little ETL routine. It's 2 lines long. It extracts a number out of a JSON blob. And here's a unit test for it. And here's what happens when it hits production data. It encounters data variance, which is a root cause of problems, right? We've all been there. And so we do what coders have been doing for a long time. We drop in a print statement. Very sophisticated. Not very sophisticated maybe, but very effective, and some very sophisticated people find it very useful for them. So I drop in the print statement, and you'll see there that I observe the program state. And I would imagine that most of you reading this code are able to see the problem. There's a none in there in production data. And by observing the program state, I identify the problem. And to identify the problem is to see the solution. That's what it means to know how to code. These 2 engineers here are 2 people to whom everyone in this room owes a great debt. They brought us Unix and C. We all rely on their work. And when we're coding in Python, we have 2 particular connections to this picture. The first is that Python was designed to be a better Unix shell for doing coding work, so it was explicitly designed in this tradition. The second is that Python was released more or less in its current form closer in time to when this picture was taken than to today. So when we use Python, we are engaging in a very old tradition. This picture was taken in 1970. When we use the Python interpreter, we can go back to 1962, the invention of the Lisp REPL, where you type in a little code, have it read, evaluate, see what's going on. And in turn, printf debugging, I was able to trace back in a published book to 1951, which is 5 years after the first electronic universal digital stored program computers were turned on, and it was documenting practices that stretch back to at least 47, let's say. So we've been doing it exactly the same way for over half a century since we started doing this work at all, since almost none of us in this room were born. Now we have notebooks, and notebooks are wonderful, and we've heard a lot about notebooks in this conference. But the thing about notebooks is that, like the shell on the left, they sit on top of the Python interpreter, right? They change a lot in terms of our productivity. They're wonderful, they're great, but they're not changing the underlying programming model. There's our model. Here's a notebook, but something very different is happening. Here I've made 2 Python method calls, and I have a live handle on approaching a petabyte of data, which I'm going to slice and dice by orchestrating 30 beefy nodes, almost as beefy as the ones that Thompson and Ritchie were using. And now there's a whole bunch of things happening under the hood of my little notebook that were not present in the old world and in our old tradition where we learned how to code. So the bottom blue box is my notebook. It's still forwarding little strings into an interpreter, but that interpreter is receiving them over an SSH tunnel into my cloud provider of choice. And in turn, the Python interpreter that finally reaches is merely a child of, in this case, because we use Spark, a large JVM structure. If it was Dask, it would be a Python metastructure. The point is there's a metastructure there. It's orchestrating other nodes. Anyone who knows Spark knows that this diagram is grossly oversimplified. And of course, looming over all of it like some gigantic sun is this immense world of data that I'm trying to work through. And the thing about immense looming suns is that our minds can't actually grasp the shifts of orders of magnitude, right? I won't belabor this point in a room full of scientists, but this is a lovely infographic in which the largest object in one panel becomes the smallest in the other. And it's an admission of defeat, right? This is a way of saying we can't actually put all these objects, Aldebaran and Sirius and Mercury, on the same image and see them. It's not possible. There aren't enough pixels to do it. Either one falls off or one blows out. And similarly, although on the one hand in cell number, is it 1? Yes, 1, I've got a Python object, right, that's in front of half a petabyte of data. When I go to print it, fortunately or unfortunately, I don't get the entire 500 terabytes of data on my screen, right? Instead, what I get is a description of this thing. So Python is there's a cognitive dissonance here, right? This is not a variable. Instead, this is more like this microphone that I'm talking into where I go, hey, go do stuff with my data. And a command goes out into that giant framework you saw before, and something either does or doesn't happen. Now it's really powerful, right? So I call this where method, that's a Python statement, but it's a Python statement that is deliberately echoing SQL because what it's going to do is it's going to take the string I've sent in, which says get me the most recent week worth of data, and it's going to set it into a compilation engine that's going to turn it into a bunch of JVM procedures that's going to go out and orchestrate all these nodes and set all this stuff up. And it's really cool, right? I got 54 billion rows, and it took about 2 minutes. You don't see the timing data there, but that's about what it took. And that's great. But I don't really know what's going on. So here I'm going to count the whole thing, and the whole thing represents about a year of data. And the last time I checked, the ratio between a year and a week was not 3 to 1. But that's what my numbers seem to be saying to me. So I'm getting an unexpected result, which is, if you've ever done distributed big data computing, is something that happens all the time. This is a fundamental symptom of a problem that you encounter. And a technique, ironically, which I think highlights the difference that you're strongly encouraged to use if you develop in Spark, if you go to any Spark tutorials or other distributed computing techniques, is the first thing you do when you're doing distributed computing at scale is you undistribute and downscale. So this method take is going to pull in data from the cloud. I can't control which rows, but I'll get a few. And that's going to enable me to use my old tools that I understand and that work really well. Awesome. What could go wrong? Well, apparently I can't even invoke the simplest method without causing a problem. So we have this project in Mozilla called E10S, and I'm trying to get information about how, on the beta channel, how experiments are going and see if the users like it. And take is blowing up right away. And I still get a traceback in this case, but my traceback, my distributed big data traceback is kind of big data itself. It's long and hard to read. And you laugh, but it's actually a skill. And there are actually people who know Python who encounter these things are like, I don't know what the traceback says. But that's a skill you figure out over time. And at the heart of this traceback is this line. Does that remind anybody of anything? So yeah, this is the same problem I saw before. I've got this, no worries. I just need to test for none, no problem. And I can redistribute my call and call take, and I get back my data. So maybe I'm okay at this after all. Maybe things are going all right. So 2 symptoms, tracebacks and unexpected results, and 1 root cause so far. I said I was going to give you a taxonomy. That's the beginning of it. Why was I able to debug that? I'm giving you trivial examples so you can see the structure. I did not display the program state. Hold that thought. Let's try take on the previous issue. Let's see if take is a sawzall that'll solve all our problems. So I'm going to take some data here from the last week, and And in cell 9, you'll see I print out some of the dates that I took. And in cell 10, you'll see that the date I used to do the selection was different. Oh, so if I just format it correctly and redo my where command, I'll get 2 billion rows, which is the correct proportion. And yay, I'm on a hot streak here. I fixed 2 problems in a row. But notice that with the second problem, I did not display the program state. Instead, it so happened that the problem state was present in every row. So just by taking a few rows, because the problem was everywhere, it didn't matter which row I got. It was going to show me the issue. And these are 2 techniques that most people will figure out on their own or pick up from a intro tutorial on distributed computing at scale. Simple, simple stuff, but my goal here is to give you a mental model for it. I assert that in our coding community, the core technique that a dozen or so of us have come to rely on in various forms is that we localize the problem state to make it observable. That's how we debug and move forward. And what I am asking you to do is to ask yourself, does that make sense? Or alternately, what the heck is he talking about? And number 2, if you've done this work before, I want to know, does that sound like what you do to overcome problems and get things done? So there they are, problem states, not program states, localized so that they can be observed. All right, let's be productive. Let's do some software engineering. I'm going to put my function in a module down there at the bottom. I've entered it onto my local file system. And I'm an engineer, so I do tests. And I've got a PowerPoint-compatible unit testing framework here that overloads the Python equality operator. And I import my module, and I test it, and it works great. So let's ship it. And I should have gone and gotten that engineering certificate because I haven't quite figured everything out. So what I've done here in the second line of cell 20 is I've distributed just the data that I used to get the test to pass. And then in the next 2 lines, I have executed just the code that was tested. And it blew up, even though we just saw it work. So what's going on? Does anyone see the problem already?
No import.
Yeah. So I've got an import error, which is nuts, right? I just saw that I could import it. That doesn't make any sense. But if I look at the line above it, it's talking about pickle, which is Python's object serialization format, and that's what Inspector Clouseau would call a clue. And then I'm reminded that, oh yeah, when I distribute, I'm executing in those Python workers on the top and on the right. And when I dynamically created my module, I created in the file system in the node on the left. And so my cluster was the framework was in a heterogeneous state, and that was another root cause of problems that you can encounter. So when you're confronted with a mystifying traceback, it's one of 5 things you can look for. So I can fix that pretty easy. And in turn, that allows me to complete what I'm calling the core technique, which is that when you go to distribute and go at scale, scale out and up. First distribute, and then scale up, and do so in steps, so that you allow problems to emerge in sensible, coherent steps. When you scale up, if you've got scaling out working, I offer these 3 buckets for thinking about the problems you encounter. The first bucket is a traceback indicating the kind of problem we've already seen, where you're calling string on a string method on a none object, or other your code conflicting with your data. The second one is the very large bucket of things are taking too long, which we're all intimately familiar with. And then finally, there are tracebacks which are a different kind of thing, which I'll discuss briefly in a minute. So let's say we have this problem. I'm going to stick with the same example so that we don't have new cognitive load. So let's say our code has been running for months, and we've processed 10 to the 14th rows. And one day, we get a traceback. And let's say we cannot determine, just by reading the traceback, what it was. Well, now we have a big problem, right? If we call take, we know that the overwhelming likelihood is we're going to get back rows on which our code worked, right? Because our code has worked on 10 to the 14th rows. But somewhere out there, there's data that our code doesn't like. So how are we going to find only the rows that cause the problem? How are we going to localize the problem if it's hiding in this galactic scale universe of data? Well, the good news is we already know. We already have a routine that reliably detects problems. It's just that usually it says no problem here, no problem here, no problem here. So we just wrap it in a try except. If our code works, we return false or none or something falsy. If our code breaks on those rare occasions, then we return that object. And that gives us a filter for problems that we can localize and observe and continue to use the core technique to move forward. Next, root cause. This is a real ETL routine. Do not try to read it. I am guilty of committing it. Do look at the white space, though. So white space is syntactically significant, and every indentation just about represents a shift in control flow, which in software engineering is called a cyclomatic complexity point. And people have established that if you have a cyclomatic complexity in your routine of greater than 10, the odds that there's a bug lurking in there start to increase sharply. And I've clearly crossed that threshold, right? And furthermore, I've kind of made it worse because a lot of those indentations are try-except blocks, which means that errors are being swallowed rather than causing tracebacks. And as I wrote this, I had some mental model of what was going to happen. And some of those exceptions are things I expect to pretty much never happen. But as we've emphasized, I can't actually imagine 10 to the 14th rows of data and what they're actually going to do as they flow through 10 to the 14th times through this control flow graph, right? I can't do it. I need to figure out some way to localize that state of which of these edges in the control flow graph are hot and which are very cool, which are going to be executed all the time and which are going to be rare. Because if I can't do that accurately, then my ability to predict what my code is going to make of my data is going to be 0. Fortunately, what I can do is I can put a global atomic counter on each edge of the control flow graph. In Spark, it's built in. In your framework, you'll have to check. It would be pretty straightforward to simulate one with Redis. But what that gives me is an ability to say, oh, this try-except block where I thought the exception was never going to happen, actually it happens 2/3 of the time. And again, that's a technique for dealing with unexpected results. So you run your code, nothing breaks, and you look at it and you're like, no, that can't be. Well, count your control flow graph and see if you just didn't understand the shape of your data. For slowness, root cause number 5 is kind of the not root cause. It just means you've just got a lot of data and you need to do a lot of computing on it. Root cause number 4 is exponential behavior. I'm going to touch on this very briefly for want of time. First off, in the case that is common in my world where you're counting uniques, you're comparing everything to everything, you want to partition your data according to whatever it is you're comparing on and tell the framework about it so that the comparison can happen quite quickly. And this is just a few lines of code in Spark that do that. It's the concept that matters, not the code, so I won't dwell on them. I also want to say a word about exponential algorithms. So when mathematicians claimed computer programming and started turning it into university classes, one of the things they did was they taught us that exponential runtime is bad, right? So you learn in CS that if I'm looking here, I'm standing here and I'm watching my data scale linearly and my runtime increases exponentially, then I'm very sad because it means I chose the wrong algorithm. I want to argue that this is a matter of perspective and that if you do a 180 and watch your data size decreasing linearly, you will watch your runtime decreasing exponentially, and you can turn your frown upside down and be very happy. This only works if your processing function is associative, and it's the kind of thing that is so stupid simple it's almost embarrassing to mention in this august company, but it's actually a very practical technique that doesn't naturally come to people's mind all the time, in my experience, PhD or no PhD. Finally, speaking of PhD, here I have attempted to compress the field of statistics into a single PowerPoint slide. This is lossy, but beyond hubris, this is very lossy compression. But sampling is another core technique that we can use. Enough said about that. The less said about that on my part, the better. And finally, there's spending. Spending just means you're doing everything else right, as far as you can tell. One final note about recognizing toolchain panics. This comes up quite often. Somebody has a traceback and they're looking for the problem in their data, and they haven't sort of brought to mind the idea that at the heart of the traceback is some complaint from their framework, meaning that something broke, which means a load problem. Notice that when you have a toolchain panic, which are toolchain specific, so I won't go into the details of the Spark ones, you need to determine whether your toolchain is just resting or has joined the query invisible, and test its heartbeats and possibly restart it and all that. And that's toolchain specific, so I won't get into it. So that's the mental model I'm asking you to evaluate. Have you seen symptoms other than these three? Tracebacks, slowness, and surprises. Have you seen root causes other than these five? Do these five cover the field in your experience? And have you used anything resembling this core technique? And does it make sense to you? I wanted a snazzy graphic here. So this is the same slide, but transferred into like PowerPoint-friendly business book stuff. Not really, actually. So one concern I have is that this talk I'm giving, I'm furthering the problem that I'm calling out, which is this is another sort of semi-formal, semi-structured way of transmitting knowledge. And so I threw up on GitHub an attempt to codify this and make this something that we could use diffs and PRs with. Can we take the craft of coding and turn it into something that is transmissible in a structured form that we can evaluate to ease the cognitive load that Gail was talking about yesterday? So on the left here, you see a little bit of the dot programming language from GraphViz, and on the right, you see a flowchart for a decision tree of what to do. And the one I've chosen is just the normal printf debugging. It fits well on the slide, and we all understand it. And what I want to know is, for the more general case, is this an effective way of transmitting coding knowledge so that we can all save ourselves times? And if not, what would be better? Because my assumption is there's something else that would be better. Oh, and one more thing. In the case where you have unexpected results, and you double check everything and you check your control flow graph, you want to remember the possibility that your code has brought you new knowledge about your data, and you have a reportable result, and you've done a great job. Thanks.
Any questions? If you have any questions, can you please go to the mic? Wait, okay, means I get a question. Oh.
So thanks, that was a great talk. I think that maybe one of the pieces in distributed computing that's a challenge that I didn't see represented here is that actually the infrastructure can be one of the big challenges in distributed computing environments, and that can lead to all sorts of, like your InfiniBand and your networking and layers of the system that you're not even thinking about as a distributed systems programmer. That can be a big challenge. But otherwise, yes, I spent 15 years doing this, and this, if I started with that, I would have not taken years to learn those techniques that you've described.
Any other questions? Oh.
So I think I've heard one definition of distributed systems as being one where a computer breaks that you didn't even know existed.
Awesome.
So in this framework that you've outlined, you seem to have really good operational knowledge of the tools that you're using and what's laid out. And what advice do you have for discovering that, like as an end user coming in, where I don't know sort of all of the levels that I'm sitting on top of?
So great question, Paul's question, and it reminds me quite a bit of this gentleman's observation. So yes, there's a fundamental problem with this presentation I've given, which is I'm trying to abstract away from that stuff. And what you are both correctly and very graciously pointing out is that no, you moron, that's actually the problem. So yeah, you have to learn it, but that kind of learning maybe doesn't scale. So because we're Mozilla and we have a budget, we hire people whose full-time job is to know that stuff. But you're quite correct that the people who go to use it find themselves becoming professionals in the framework, or else they don't get anything done. And so I actually would ask you to evaluate this work. And again, I did this very quickly. There's zero chance that this is the right way to represent this knowledge. But what I want to know is there any promise of us as a community doing what, do any of you know Mark Guzdial? He teaches computing, he teaches the teaching of computing science. And he talks about, I'm gonna forget it. Sub-goal labeling, meaning you put a name on a technique, you put a name on a problem and all that. And so what I would ask you to is that, yeah, when you go to learn a framework, can we take that learning and put it into some form that is actually easily transmissible? Because all these frameworks have tons of docs, right? And they all have heads-up displays, right? And we just heard a presentation, I only caught the second half of the gentleman who's showing really impressive work with Dask. But the question is there a more efficient way to transmit that knowledge and to kind of chunk it so that you can focus on your science and not on becoming an expert in the framework?
Hey, so I think I might be making the same point again, but one of the issues that I have is that I find that the practice of software design, this is not specific to distributed or anything. I do a lot of fairly serious object-oriented development, and one of the problems I have with debugging, and the reason I often resort to printf debugging, is because failure breaks my abstractions. So I can't use my design tools to interrogate the failure modes at all. What I end up doing is trying to figure out what the control flow is, but the design is not around the control flow, it's around the objects and their scopes and all of that stuff. So I guess you have the same issue here. And so one of the things that we might try to think about is how to design software in a way where failures are sort of more transparent, like what happened.
Absolutely.
Anybody else?
No one will tell me that there are errors up here because I know there are and you know there are.
So my colleague here reminded me, I made a comment and didn't ask a question. I actually have a question version.
That's all right.
Which is, so for like 40 plus years, multi-user operating systems are supposed to provide us with like a encapsulation system so that as programmers we can write stuff that is isolated from other pieces. And now we've got containerization. Do you see that containerization is providing us with something new that addresses these challenges so that you can think at the level you've been talking about here, so that the kind of comment I made and the comment of somebody else, that the infrastructure problem goes away? Like what are your thoughts on containerization and operating systems as functionally providing the necessary level of isolation?
So great question. Will containers provide the kind of solid abstractions that hide this complexity in fruitful ways? I've had 2 conversations about that already this week. My answer is I don't know because I'm not a container guy. It sounds a lot like what Alan Kay talks about when he talks about TCP/IP as the only true object-oriented system, in the sense that he meant it when he invented it, where when you send a TCP/IP command, what's behind it is in principle a full computer. And so everything you deal with is a full computer, right? And I think containerization is moving towards that. It seems clear to me that we haven't gotten there yet. Just as an observer of containerization, somebody who relies on operations people who work with containers. It also seems clear that it would make sense, but I haven't seen anyone demonstrate it. And if anybody in the room has seen anyone demonstrate it, don't be shy, grab a mic.
All right, so let's thank Sam one more time.